Our first congruence postulate is side-side-side congruence postulate. If three sides of one triangle are congruent to three sides of a second triangle, then the two triangles are congruent. Right, so for instance, here in our example, if side AB is congruent to side FE, those are the sides with one congruence mark, and side BC is congruent to side ED, those have two congruence marks. Didn't want to move them. And side AC, there we go, is congruent to side FD with three congruence marks. Then triangle ABC is congruent to triangle FED using side-side-side triangle congruence postulate. This is only for triangles, right? It would not apply to other figures, right? For instance, squares, if I could have a square where all the sides were 5, and I could have a rhombus with all the sides are 5, and those shapes wouldn't be congruent, right? So this is only for triangles. So if three sides of two triangles are congruent, then the three angles will also be congruent. Note that the points must be given in the correct order, so corresponding parts on each triangle are matched. So for instance, triangle ABC is not congruent to triangle EDF. Right? So here we have, so although ABC is not congruent to triangle EDF, if I wanted, for instance, triangle CAB, that would be congruent to triangle DFE. Right? So let's look at using constructions to copy a triangle. Because if I copy the sides, right, I have two congruent, I'll have the same triangle. All right, so follow the steps below to construct a triangle that is congruent to a given triangle ABC. And of course, I didn't use that one up there because, well, it's too small for me and the compass. But I'm going to use a triangle I have down there, that other triangle ABC. Our first step is actually going to be copying a segment. Actually, going to copying three segments. The first segment is easy to copy because we just have to copy a segment using the same construction rules that we learned back when we were learning constructions. And that first step is you need a segment to copy the segment onto. And then secondly, switch that the other way. Oops. We're going to measure our segment using our compass. And that's of course too big. So let's close it up a little bit. Now it's too small. Unfortunately, every time I put my hand on the board, my shadow is blocking me. I think that looks like in the right position, especially if I move this one here. All right, so let's draw our arc. All right, looks pretty good. We're going to copy that same mark over here. I guess we should give ourselves a point, but I'll use the edge here, and then I'll put a point on it. So there we go. All right, we've copied our arc. All right, so now we have a segment that's congruent to AB. I guess we could call this one DE, just like the picture above. All right, so now we need to copy the other two sides. All right, well, if we use our compass here to draw a radius of a circle, right, we can know where to put our sides. All right, so first of all, so my compass here, right, that distance represents the radius of a circle. I'm going to close this up. Oops, I'm not going to do that. Oh, now we got a random mark. And unfortunately, I cannot reach the compass. So what if I turn it the other way? So we're trying to somehow measure, I can do this, segment AC. All right, so the compass spread is going to represent the length of AC. There we go. And notice that AC here, oops, is going to be the radii of a circle. Right? It's because if I were to swing this around, I've got a circle. All right, that looks good. All right, now I'm going to copy that very same segment over here. Well, the arc anyway. I can't just draw the segment because I don't know where to put it. And I can measure it, but if I don't put it in the right place, then there's no way all my three segments are going to intersect. Right? But so there we know we've got one marking. If I do the same thing, but from point B, I'm going to have the distance that it is from point B. And together, those two distances are going to tell me where to put point C. Right? And once I know point C, we already know where A is, right? Or D is. That's already marked. E, we measured. All we need now is F, the last point, and that's going to go where C is. All right? So if we have the two distances from D and from E, that'll put it in the right spot. And I think that looks good. Oh, that's not what I wanted to do. All right, let's try this again. There we go. All right, there's our other arc. We're going to copy that same arc, this time from point E. There we go. And all we need to do, whoops, well, it doesn't matter if I close it now. I'm done. You're gone. You're done. All I need to do is take out a line tool. We need to draw a line from D to this point here. That's F. I'll label that. And then from E, and I just missed E, and to that point F. Let's fix that. E there. Just kind of missed it. And there we go. I still missed it. We have copied our triangle using a construction, right? And copying three segments, right? And because we measured it from both points there, it had us put F in the right location. And look at that. And you can do that as well. And I believe you've got the steps in your notes. Right, let's look a little bit more at side, 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 triangle congruence. Moving along, come on. Oops, we have an extra page here that we don't want that. All right, I had half of it one in there. All right, so we're going to prove side, side, side congruence criteria. If three sides of one triangle are congruent to three sides of another triangle, then the triangles are congruent. All right, so we're given that AB is congruent to DE, and BC is congruent to EF, and AC is congruent to DF. We want to prove triangle ABC congruent to triangle DEF. So to prove the triangles are congruent, we're going to find a sequence of rigid motions that maps triangle ABC to triangle DEF. And we're going to complete the steps of the proof here. This is going to be an informal proof. All right, so we want to move ABC to DEF. All right, so first of all, we're going to need to notice that they're basically mirror images of one another. All right, so what if we reflect about this line? And we can give it a name. Let's have it line N. All right, so our first step is to reflect triangle ABC over line N. And you can always draw a line anywhere you want. It just connects 2 points. Right? Right, so I'm not gonna construct this one. Right, so I'm just gonna kind of draw it freehand best I can, because this is just a model. I'm not drawing the exact triangle, which is good because that's not even close. So I can fix that side a little bit. It could look a little bit more congruent. All right, now we'll call that good. All right, so there's our reflection. So this would be C prime. This would still be A prime. It wouldn't move. And this would be B prime. All right, and notice that we're not quite there yet. All right, we're facing the same direction at least. All right, but we're not quite there. We need to translate. It's kind of hard to figure out how many units, but we could talk about direction. So we're going to translate triangle ABC. It's going to go right and up. Right? And so since there is a sequence of rigid transformations, that maps triangle ABC to triangle DEF. Triangle ABC is congruent to triangle DEF. And in this case, because the sides are congruent, right? We have all three sides are congruent. It would be using sides. We could also use side, side, side triangle congruence. And that's what we're going to be learning about, how to use side, side, side triangle congruence as a congruence shortcut. Right? So here, I think we have one on the coordinate plane. I think that's the one that's next. It is. And all the work's been done for us because we've been already working with the distance formula when we were working with area and perimeter. Right? So to find the distance of a line that's not horizontal or vertical, right? You take the difference in the x-coordinate squared plus the difference in the y-coordinate squared. Right? The squaring there gets rid of the negatives, but because you've squared it, you've made the distances more, right? And you've got to take the square root to undo the squaring process. Right? So here it's been simplified out for us. RT is equal to square root of 18, or 3 square roots of 2. Right? RT is in the triangle on the pre-image there. Right? And then if we look at JK, right, JK is also 3 square roots of 2. That means that we have, first of all, we have RT congruent to JK. And actually, technically, because we're not talking about measurements, we're talking about a side, they should have those, the line segment symbol. So you can put that on yours in your notes. And then if we look at TZ, right, TZ is the square root of 17. That isn't simplified. KL is also the square root of 17. That means that TZ is congruent to KL. And then finally, RZ is congruent to JL. They're also both the square root of 17. So actually, not only is these triangles also happen to be isosceles triangles, right? Because they have two sides congruent. So they're both isosceles triangles. So RT is that now it's the measure. That's why there's an equal sign and no line segment. RT is equal to JK. TZ is equal to KL. RZ is equal to JL. By definition of congruent segments, all corresponding segments are congruent. Right? We have if you're congruent, if you have the same measure, you're congruent. Therefore, triangle RTZ is congruent to triangle JKL by side, side, side. Let's also talk about what sequence of rigid transformations maps triangle RTZ to triangle JKL. Notice they're mirror images of one another. Right? They're not in the same location. If I were just to reflect, they wouldn't match up exactly. But if we reflect and do something else, they would. Right? So I'm going to have to reflect over a vertical line. We can see that a vertical line would be in between there. You really could reflect over any vertical line because no matter what, you're going to have to translate. You're not going to be able to match, for instance, Z to L. Right? So why don't we just reflect over the y-axis, right? Also known as x equals 0, right? Same thing. All right, so what sequence of rigid transformations maps triangle RTZ to triangle JKL? This is not the only sequence of rigid transformations. This is one type, one example. All right, so I could reflect over y-axis and put this in your notes. Which is also x equals 0, right? And when we do that, xy would go to, so if we reflect over a vertical line, right, x becomes the opposite, or I should say x changes and y becomes the opposite. Excuse me, let's try that again. Back that up again. X changes and y stays the same. If the line that you're reflecting is that vertical line you're reflecting over is the y-axis, then x is the opposite and y stays the same. There we go. All right, so if we reflect over the y-axis, actually we can write it over here. All right, so we're reflecting our pre-image, which is triangle RTZ. All right, so R is at 2, 5. That would go to negative 2, 5. And Z is at 1, 1. That would go to negative 1, 1. And finally, T is at 5, 2. That would go to negative 5, 2. So let's draw that one in. All right, so we have negative 2, 5. There we go, and that's going to be R prime. And then negative 1, 1 is Z prime. And then finally, T is at negative 5, positive 2. And so there's T prime. So we'll draw our triangle. So now we see it's facing the same direction. Kind of squish my line in there a little bit. I could maybe make it nicer. Of course, it's all stuck together. Let me try and fix it up just a little bit. All right, so that was 2, 3, 4, 5. That's where T prime was. And let's try to draw that nice this time. Well, that's certainly a little bit better. Now we can see that it's facing the same way. And if we match a pair of corresponding points, right? So if we look at the congruent statement, Z goes to L, right? Z here goes to L, right? So Z prime only has to go 2 to the left and 1 down, right? So we would have a translation. And let's write in coordinate notation. By the way, I'm right near extend a page. It's probably going to extend my page. I'll try to just kind of go around it. Yep. But no. Extended my page. So it got a little smaller. That's all right. I think you can still see. All right. So X is moving to the left, 2 to the left. So it's going to be X minus 2. And then Y would have to move 1 down. So Y minus 1. That's our sequence of rigid transformations. That's going to map our triangle RZT to triangle JKL. Right? So that's the end of this podcast. We'll look at another type of triangle congruence, as well as do more practice with side, side, side. Right? Let me just double check, but I'm pretty sure that is where I wanted to end. Let me just double check. Well, Spinning Ball says, oh, that was not where I wanted to end. I wanted to say one more thing. It's a good thing I checked. All right, so proving triangle congruence on the coordinate plane. All right, that was kind of the end of side, side, side. We'll see side, side, side in the next podcast or the podcast after it. But I did want to go over how to prove triangle congruence on the coordinate plane. You have 2 choices. One is to use the distance. This says formula. It's a little messy there. It's like my words were going downhill. My board was wigging out a little bit. I don't know what color I wrote in. I guess that's maybe like navy or something. But we're going to use the distance formula to show that corresponding sides are congruent. Or we can identify the rigid transformation that maps one triangle to the other. For instance, triangle ABC to triangle A prime, B prime, C prime, which would probably write one triangle to the other. In the last example, we did both. Sometimes we'll do both. Sometimes we'll just do one. All right? So thanks for watching and bye for now.